Alright, welcome back to our online class. Today we're going to be talking about drag. So our goals are to talk about what the effects of drag are on an aircraft, the different types of drag, how to minimize drag, and how we can actually calculate drag using the drag equation. And then we're also going to talk about the lift to drag ratio and its effect on the aircraft's maximum range and maximum glide distance. Alright, so I'm sure everybody remembers the four forces of flight: lift, weight, thrust, and drag. So just a reminder, lift is what pulls the airplane into the sky. It's created by the wings or the rotor blades of a helicopter or drone. Lift, by definition, acts perpendicular to the relative wind or line of flight. Weight is the force of two masses being attracted to each other. So that's what's pulling us down to the center of the earth. Thrust is created by the jet engines or propellers of the airplane. Thrust is the push that moves the aircraft through the air. Drag is the resistance or friction to things moving through the air. It's caused by particles bumping into the object or our plane. So you can think about sticking your hand out the window of a car when it's moving, and that gives you a good idea of what drag is. So I kind of just discussed all this in the last slide, but you can read through it. So the only question we didn't really talk about is when might drag be a good thing. So you might say drag might be good to slow your airplane down when you're landing, so you can come to a stop. So a good pilot needs a solid understanding of drag because it's important for safety and performance. So to ensure safety, a pilot may need to demonstrate how to reduce drag in critical situations, such as climb out, go-arounds, and aborted landing, and recovery from a stall. In terms of performance, good pilots know how to reduce drag to fly more efficiently and to understand the effects that it might have on the airplane during flight. So we're going to watch a quick video of a Cessna 180 making a short landing, so to show you that drag can be a good thing. Alright, so the two types of drag here are, we got parasitic drag, which is the resistance to forward motion caused by the aircraft's shape, construction type, and material, and induced drag is a result of an airfoil developing lift. The total drag on aircraft is a combination of parasite and induced drag. So we're going to be talking about those two types. Alright, so the first type, parasitic drag, is a part of the aircraft that is caused by any aircraft surface that deflects or interferes with the smooth airflow around the plane. The faster an airplane flies, the greater the parasite drag. If you double the airspeed, the parasite drag quadruples. For example, an airplane has 4 times as much parasite drag at 160 knots than it does at 80 knots. So we're going to watch this video.
Parasite drag is a direct result of the air resistance as the airplane flies through the air. There are 3 types of parasite drag: form drag, interference drag, and skin friction drag. Form drag results from the turbulence created as the air tries to flow around the aircraft. Aircraft with larger cross sections will have higher drag than thinner, more streamlined designs. Other items, like the landing gear and the antennas on the aircraft, will also create form drag. Interference drag occurs in locations over the aircraft where different surfaces meet. For example, where the wings attach to the fuselage. Placing 2 objects close together will create up to 200% more drag than if each object were separate. To minimize this, manufacturers will place smaller, angled pieces at these locations. Skin friction drag is caused by the rough imperfections of an airplane's surface. A good example of this are the rivets located on the airplane's skin. These bumps disrupt the airflow from otherwise flowing smoothly along the surface. Keeping the surfaces clean and waxed, while also utilizing flush-mounted rivets, will minimize the production of skin friction. The amount of parasite drag varies with the speed of the aircraft. As the airplane's speed increases, the amount of parasite drag will also increase. In fact, the amount of parasite drag you experience is directly proportional to the square of the airspeed. For example, an aircraft traveling at 120 knots will experience 4 times as much parasite drag as the same plane going 60 knots at the same altitude.
Alright, so brought up form drag. So form drag, it's generated by the shape of an object in relation to the relative wind. Air separates around an aircraft and its components and rejoins after passing. So a more streamlined shape allows the air to rejoin faster with less turbulence and reducing drag. So what parts of the aircraft might produce the most form drag? So hopefully you're thinking, well, the largest, flattest surfaces will produce the most form drag, like the fuselage, and the wings create a lot of drag. Landing gear that doesn't retract, big wing struts, or floats would all be creating form drag. Alright, so now interference drag is generated by the mixing of airflow streams between the airframe components such as the wing and the fuselage, or landing gear struts and the fuselage. So as air flows around different aircraft components and mixes, the turbulence that is formed creates a drag sum greater than the drag components would have by themselves. So one example of interference drag is the corner created by the junction of the wing to the body of the airplane, also known as the wing root. 2 currents of air, one traveling over the fuselage and one traveling over the wing, meet in a turbulent collision. Perpendicular angles like this are particularly bad for interference drag, so designing vertical components away from the wings can help. In addition, fairings can be used to smooth out one junction and reduce the interference drag, like we saw in the video. So skin friction drag is the resistance of air moving across the surface of the airplane. On a very small scale, the surface of an airplane is rough, like sandpaper. If you run your hand over sandpaper, the sandpaper catches your skin and slows down the movement. Same thing happens with an airplane. The skin of the airplane catches the air particles next to it and tries to pull the air particles along. The behavior of the boundary layer is key to the function of the airfoil. Layers of air just above the wing's surface move slowly, while those further away move faster, until finally higher layers move freely at the free stream velocity. The layer between the surface and the free stream velocity is the boundary layer, which acts almost like a physical surface in terms of the airflow's interaction. This creates an invisible, effective shape to the airfoil and affects lift and drag characteristics. So we'll watch this video to see that.
Skin friction drag occurs when airflow surrounding an object is disturbed by imperfections in the surface or skin around which the air is flowing. For example, competitive swimmers wear swim caps, fitted swimsuits, and shave their hair to have smoother skin. These tactics reduce overall swimming time because they're cutting down the amount of resistance in the water. If a swimmer did not cover their head with a cap, or if they wore a loose suit, the athlete would have to work harder in order to overcome the resistance. With less resistance on their bodies, swimmers are better able to overcome a lot of the skin friction drag. Similarly, an aircraft also meets resistance when its surfaces are not smooth. When viewed at a molecular level, every surface, regardless of how smooth it appears, has some level of roughness. This aircraft is no different. Look at all those surface irregularities. Skin friction drag is the aerodynamic resistance due to the contact of moving air on the surface of the aircraft. To understand skin drag further, let me show you a few things about the space called the boundary layer. For this example, we'll look at an arbitrary section such as the upper portion of the right wing. The boundary layer is really thin. At most, it's about the thickness of a playing card in level flight. For our purposes, we'll break it down into 3 sections. These are the laminar boundary layer, the transition region, and the turbulent boundary layer. Let's go through an example to see the path of air molecules through the boundary layer. In flight, the air molecules that come in direct contact with the surface become virtually motionless for a brief moment due to surface roughness. After the stagnation point, the air molecules continue along its path. As the flight progresses and molecules move rearward past the leading edge and laminar boundary layer, the molecules enter the transition region. The transition region is identified by an increase in height and has more turbulent swirls as compared to the laminar boundary layer. Molecules farthest away from the wing surface tend to move at faster velocities and are least affected by the turbulence of the boundary layer. These air molecules are in a free flow zone and contribute a minimum amount of drag. Now, at some distance behind the leading edge, the smooth laminar boundary layer breaks down and transitions to a turbulent flow. In the turbulent boundary layer, I want you to remember that airflow separation is at its greatest, producing the highest amount of drag, which ultimately destroys your lift. Just like the swimmer, you can reduce skin friction drag by making sure your aircraft is smooth and clean, ensuring it's free from dirt, bugs, ice, and debris.
So at home, you can try the Student Activity 1 that's in your guys' book that I made for you if you have the materials. So you can look over that and try that. Alright, so let's talk about induced drag. So this is also called lift-induced drag because it is an inherent part of production of lift by the airfoil. No system can be completely efficient, including lift production by a wing. The inefficiency in lift production is induced drag. To produce lift, the airfoil is tilted in a positive angle of attack. The lift produced by the airfoil is always perpendicular to the relative wind. Since the relative wind follows the upper curve of the airfoil, the produced lift is not vertical, but tilted backwards. This real lift can be described as a vector with a vertical component, and a horizontal rearward component, the induced drag. So unlike parasite drag, induced drag is a byproduct of the airfoil's production of lift. So, as you guys recall, an aircraft must constantly produce the correct amount of lift to counterbalance the weight of the aircraft. As the aircraft accelerates, it produces much more lift since lift increases with the square of increasing velocity. To avoid this unwanted excess lift, the pilot lowers the pitch of the aircraft to maintain level flight and therefore the angle of attack to maintain a constant amount of lift. So if you look at those diagrams, it's apparent that reducing the angle of attack also reduces the rearward component of lift, meaning there is less induced drag at lower angles of attack. Since low angle of attacks correlate with high airspeed, students, you guys should see that the induced drag decreases with increasing. So as you guys learned when we were talking about lift, generating lift creates a high pressure area below the wing and a low pressure above it. The high pressure area below the wing seeks to fill the low pressure area above it by swirling over the wingtip. I remember we had a video of this. So as the airplane moves forward, this creates a corkscrew-like pattern in the air. This corkscrew or vortex interferes with the downwash produced by the wing, creating induced drag. So let's watch the video example. So this is the same video we watched already. Alright, so reducing induced drag has been a goal of aircraft designers as long as there's been airplanes. One of the approaches by reducing induced drag has been to eliminate or reduce the effect of wingtip vortices. If vortices could be prevented, it would significantly reduce the drag on the airplane. Turned up wingtips, called winglets, are one of the ways designers have found to decrease induced drag. I think I remember Luke asking about that before we had to do online classes, so there's your answer. Another way to reduce induced drag is to increase the aspect ratio of the wing. Aspect ratio is the ratio between the wing's length and chord. A high aspect ratio wing is long and narrow, like the wings of a glider. It is very important to reduce drag on gliders as much as possible, right? Some wing plan forms also reduce vortices and induce drag. An elliptical wing is the most successful, but is difficult to manufacture. Tapered wings aren't as effective as elliptical, but are easier to construct, and therefore a common compromise. Alright, so ground effects. So in flying close to the ground, within half of a wingspan of the ground, that's what we'll call close, the ground interferes with the airflow patterns, the vortices, the upwash, and the downwash around an airfoil that create the induced drag. This has an effect of reducing induced drag. To a pilot, it feels like there's a cushion of air on the ground. So ground effect can be a double-edged sword on takeoff. On the positive side, it will allow an airplane to fly at a slower speed than it could outside of ground effect. This can be used to get the airplane into the air more quickly and allow easier and faster acceleration that would be possible on the ground. This is most often encountered on unpaved runways, especially runways with soft or muddy ground, that would significantly reduce the airplane's ability to accelerate and increase takeoff distance. On the other hand, if the aircraft lifts at too low an airspeed because of the ground effect, it may not have enough speed to fly outside of ground effect, which could bring you right back to the runway. So during landing, ground effect can cause an aircraft to float just above the runway, past the intended point of landing. This could be a problem on short runways or in cases where the pilot has excessive speed. An aircraft will not land as long as it has flying speed, and ground effect can make it difficult to slow down to that speed. So you must plan for the ground effect when landing. So we're going to watch a couple of videos that illustrate clever designs in the development of unusual aircraft that take advantage of the ground effect.
This Soviet creation has been dubbed the Caspian Sea Monster. Its designers believe the Ekranoplan, a low-flying ground effect craft, could ultimately replace cargo ships and ferries. More than 300 feet long and 130 feet high, the Ekranoplan was first sighted several years ago by U.S. spy planes as it participated in maneuvers outside Nizhny Novgorod, one of the most secretive cities of the Soviet Union during the Cold War. This 500-ton cargo craft can reach speeds in excess of 300 miles per hour while flying just 20 feet above the surface. It's capable of carrying 50% more weight than a conventional cargo plane of the same size and uses half the fuel to do so. One of the most unusual aircraft ever designed, it's evident that the future of flight has the potential to be revolutionary as well as evolutionary.
In Singapore, ground effect technology is alive and well. This is the Airfish. It uses a reverse delta wing to help push air downwards and maintain the air pressure beneath it. It can reach a top speed of 75 miles an hour, powered by just a tiny 70 horsepower motorcycle engine, and its 12-gallon fuel tank gives it a range of 185 miles. Batman, eat your heart out. But if wing craft are to move beyond glorified water taxis, they need to get bigger, much bigger.
In theory, wing and ground effects works
better as the craft gets bigger. So a really big craft will be very, very efficient. That's where the economics starts to make sense, and you can start to build a business out of it.
Funny you should say that. In South Korea, Jin Chung Park and his team are already hard at it.
This is a combination of hovercraft and aircraft. So we are saying this is fusion technology. That means a combination of several technologies, especially wing and ground effect.
The WFH-500 solves the problem of takeoff by briefly diverting thrust from its engines under the craft, creating a temporary air cushion before the pilot puts his foot on the gas and it's full steam ahead. The South Korean Wig Seacraft will carry 50 passengers, and plans are already afoot for the next generation, a 350-passenger beast that can carry 40 tons of cargo, which is great news for fuel efficiency. So Cold War technology 50 years on could help us with the fight against global warming.
Alright, so engineers calculate the drag on airplanes by using information about the size, shape, and speed of the airplane. Using this information, they can decide how much thrust is needed to overcome drag and keep the airplane in the air. So drag calculations must account for all forms of drag. So total drag equals the induced drag plus the parasite drag.
Generate thrust to overcome drag. Drag is the air resistance that opposes flight. It acts parallel and in the same direction as the relative airflow, and it's a relentless force that deserves a thorough flight club treatment and your full attention. Total drag consists of drag forces that are linked to lift production, known as induced drag, and those that are not linked to lift production, known as parasite drag. Let's have a look at induced drag. At high angles of attack, the high-pressure air below the wing likes to swirl around the wingtip towards the low-pressure air above the wing. A twisting vortex of air forms behind the wing, deflecting the airflow downwards. An inclined local airflow is created, which is the average of relative airflow and the deflected airflow, resulting in the lift vector tilting backwards and contributing to total drag. Now for parasite drag, which consists of form drag, skin friction drag, and interference drag. Form drag is caused by disturbed airflow that's separated from the surface and spawned into turbulent wake. The more streamlined an object is, the less form drag it creates. So any obstruction to smooth airflow, such as dangling wheels, will produce form drag. If we flatten a spherical object completely, the only drag we get now is the skin friction. As the name suggests, skin friction depends on the quality of the skin surface the airflow passes over. A laminar flow results when the airflow passes over smooth surfaces, so drag is small. But introduce wing ice or exposed rivets, and a turbulent boundary layer forms, resulting in more skin friction drag. The airflow around the wing may flow faster than the airflow around the fuselage. So where these different airflows meet, interference drag is born because they clash within the space they share. These graphs represent induced and parasite drag against the airspeed. Induced drag is most significant at low airspeeds and high angles of attack, where the pressure differential between the top and bottom of the wing is the greatest. On the other hand, an increase in the airspeed increases parasite drag by a factor of the square of airspeed. So if you double the airspeed, for example, you get 4 times the parasite drag. Do you know what the point is where the two drag lines meet? Please share your thoughts below.
Alright, so because induced drag is caused by the production of lift, it should be no surprise that it is the greatest at high angles of attack and low airspeeds. This is because at lower airspeeds, a higher angle of attack is needed to produce lift and counteract the aircraft's weight. The result is that induced drag increases proportionally to the increase of the angle of attack. Or to put it another way, the amount of induced drag varies inversely with the square of the airspeed. And the opposite is true for parasite drag, which increases as the square of airspeed. So in graph, it's easy to see there's a point where induced drag and parasite drag are minimized. For every aircraft, there will be a specific airspeed at which total drag is minimized. Alright, so here is our equation for drag. So this can be used to calculate the drag of an aircraft. But we're going to make inferences about the factors affecting drag based on the equation itself without need to make any calculations. The elements of the equation indicate what factors affect drag. These include density, velocity, and surface area. The relationships among these elements indicate the magnitude of their impact on drag. For instance, since air density is the numerator of the drag equation, we know that drag will vary directly with changes in air density. Because velocity squared is in the numerator, we know that drag will vary with the square of velocity. So let's compare the drag equation to the lift equation that we saw in a previous lesson. Note that the only difference is that the coefficient of drag replaces the coefficient of lift. This is significant because it means the same factors, density, velocity, and surface area, affect both drag and lift. And like the coefficient of lift, the coefficient of drag is specific to the shape of the airfoil and the angle of attack. So here's just an example. So if we look at this, if we hold all but one variable steady, we can see the impact of the individual factors on drag. So in this example, only the air density changes while velocity and coefficient of drag are held constant. You've already inferred that drag will vary directly with changes in density. So by calculating how drag changes when density changes, you can see the significance of this single factor in determining drag. So, I'd like for you guys to predict how the density in air will affect drag. Will the change be large or will it be small? So here we can look at the drag equation and we can see that drag is directly proportional to the air density. Therefore, when air density changes, drag will change by the same relative amount. Because all other variables are held constant, we can determine the relationship between drag at the surface and drag at 10,000 feet by dividing. So on this day, the change in air density means that at 10,000 feet, drag is 73.9% of the drag surface, a reduction of 26.1%. So, will doubling the airspeed double the drag? What do you guys think? So, the airspeed doubles, but all the other variables are held constant. So, if airspeed is doubled, does that mean that the drag is doubled too? So, looking at the drag equation, hopefully you'll see what happens when airspeed doubles. Because drag is proportional to velocity squared, when airspeed doubles, drag will quadruple. So, here is just a quick calculation. We can demonstrate the relationship between velocity and drag more precisely. So when using the drag equation, you should first convert knots to feet per second. 1 knot equals 1.7 feet per second. So you can kind of go through and see how everything's plugged in and how that all works out. So, is it necessary to know exact speeds at all? What do you think? No, not really. We can make the calculation using knots, but only because the rest of the variables were held constant. So we can determine the relationship between airspeed and drag just by looking at the equation without need for specific numbers. Alright, so lift to drag ratio. This can be used as a way to determine whether an aircraft or airfoil produces lift efficiently. The higher the LD ratio, the more efficiently the aircraft produces lift. And the most amount of lift for the least amount of drag. So I want to remind you guys that lift and drag equations are almost identical. We just saw that. The only difference is that the lift equation includes the coefficient of lift while the drag equation uses the coefficient of drag. So as a result, we can calculate the LD ratio by finding the ratio of the coefficients. So the maximum LD ratio is important because it represents the point where drag is minimized and the aircraft produces lift most efficiently. This is the point where the aircraft has maximum range and maximum glide range. Why might it be important to know how to achieve maximum glide distance? So, maybe in an emergency you need to glide to a landing. Would be a good example. Alright, so you're going to be doing student activity 2, so this is the formula you're going to want to use with student activity 2. Alright, so read these, pause it, and then we'll talk about the answer. Alright, so ground effect is the result of interference of the surface of the earth with the airflow patterns around the airplane. Alright, so read and pause this, and we will go over the answer. So hopefully you remember that it's less than the length of the wingspan above the surface. Alright, so here's another one. Pause it and read it. Alright, so the answer is A. Induced drag decreases, therefore an excess speed at the point of flare may cause considerable floating. Alright, so this was a long lesson, but we made it through it. Have a good day.